Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving an interesting homemade equation with complex numbers. Alright, so we have this equation I to the power negative iz equals e to the power pi over 2. And we're going to be solving for z values. Z is a complex number. What is a complex number? A plus bi is a complex number. It's also the name of this channel. If you're new to complex numbers, go ahead and check out my lecture videos. And if you like algebra and number theory and or geometry, go ahead and check out my other channel called Cyber Math, Cyber with an S. Okay? And I hope you like the new logo or the profile picture. I know some people like the old one, but that looked like an old guy, so I decided to change it. And I think this kind of looks cool, but let me know what you think. Okay? Anyway, so we have this equation, and how do we solve it? We have the I at the base, which is problematic. But on the right-hand side, what makes this problem even more interesting is that we have a real number on the right-hand side. Isn't that cool? We have an imaginary to an imaginary power, which can sometimes give us real results. That's the beauty of complex numbers, the imaginary numbers, because from the imaginary world, you can go to the real world and vice versa, right? Or can you have an equation in real numbers that gives us an imaginary solution? And the answer is yes, of course. Think about x squared plus 1 is equal to 0. It's a polynomial equation, but its solutions are complex or imaginary, right? You figured it out? Cool. Now, to be able to solve this problem, you'll probably remember a while ago I made another video, but I don't want to give it away, so I don't want to tell you which video it is, but if you know it, you know it. And in that video, we actually kind of got, I think I say kind of because we didn't get the exact same thing as far as I remember, we got something similar. So that should definitely be a clue for you to how to proceed. But here's what we're going to do. We're going to write this number in polar form. To do that, we're going to use Euler's formula. And in general, in the Argand plane, I just found out that I learned, thanks to Nadia Fan, that D is sometimes silent. Anyways, you have a complex number, let's say Z, A plus BI. You can kind of plot it like this. This will be R, which is the absolute value, which is given by the square root of a squared plus b squared, the distance from 0. And there is an angle which is measured in the positive direction, which is counterclockwise. And it's called theta, and theta is usually arctangent of b over a. It's not always like that, but kind of. Let's just keep it in the first quadrant, and we should be fine. Okay? So, how do we use that information? Well, any complex number can be written as r e to the I theta. So that's what we're going to do on the left-hand side. And then I think we're going to check our work at the end because I probably remembered to include results from Wolfram Alpha. Most of the time I remember. Sometimes I forget. And then we're going to go ahead and check our answers too. Now, how do we use this information? Do we replace z with r e to the I theta? It's probably one way to approach it. Why not, right? You can go ahead and try it. For example, replace this with r e to the I theta. The problem is we have an e. It's at the base, but we have an e here. How do you reconcile these? How do you kind of make them similar looking? The problem is with the base, not with the exponent, right? So we got to change the base from I to E. They're just letters, but they represent constants, right? Yes, we use letters sometimes to represent well-known constants. So here's what we're going to do. We're going to write this in the form r e to the I theta. We're going to start with I. How do you write I in that form? Well, think about it. I is on the imaginary axis because it is imaginary. 0 real parts. Its distance from 0 is 1 unit. And the angle it makes in the positive direction is pi over 2 radians. But of course, you're allowed to add multiples of 2 pi because that'll bring you to the same point. So we add that into the equation, okay? So here's what we're going to do. I is e to the power I pi over 2 plus 2 pi n. So we include multiples of 2 pi to make up for that period thing. Make sense? Cool. So we were able to replace I with something with the base e, which is nice because that's Euler's number, and Euler is just amazing. So now let's go ahead and replace that I with this whole thing. Okay? Not just e, but the whole thing. That becomes the following. E to the power I times pi over 2 plus 2 pi n. And then this will be raised to the power negative iz equals e to the power pi over 2. Wait a minute. Why are you trying so hard? Can't you just natural log both sides? Some people, I'm pretty sure, are going to say, hey, why don't you just ln both sides? That's going to be super easy. You don't have to worry about this, right? Don't beat around the bush. Well, if you do that, you're going to get the following. Negative iz times ln I equals pi over 2. The question is, the $1 million question. Are you ready? What is ln I, right? How do you log a complex number? That's called the complex logarithm, and it's multi-valued. So instead of that, to avoid all that trouble, we're going to use this notation. Even though it looks complicated, it's actually going to simplify. First of all, notice that we multiply I by negative I, producing negative I squared, which is positive 1. Because one thing that you should never forget, and if you look at lecture notes, you're going to see this being mentioned a lot. I squared is negative 1, so negative I squared is positive 1. Got that? So they kind of cancel out. So we're going to multiply by z, e to the z times pi over 2 plus 2 pi n equals e to the power pi over 2. Great. But now we have the same base, so we can ln both sides. This is a good time to do it. So we can end up with the exponents. And our goal should be what? To solve for z, of course. Well, so why don't we just multiply? I meant divide, right? Both sides by that. Wait a minute. Are you serious? If n is equal to 0, from here, you get z equals 1. Is that a solution? I don't know. You should give it a try. Maybe it is. Look, I to the power negative iz. When z is 1, this becomes I to the power negative I. And I is e to the power I pi over 2. Multiply by negative I. This becomes negative I squared, which is 1. And yes, it works. Beautiful. Z equals 1 is a solution. Ta-da! And the only integer solution. Okay? What about the other solutions? Here we go. These are all the solutions. Of course, you want to make it look a little nicer, so let's go ahead and divide everything by pi, or maybe multiply the top and the bottom by 2 first. So pi over pi plus 4 pi n. And then if you take out a pi, you're going to get 1 plus 4n. And then if you cancel out the pi, you're going to get z equals 1 over 4n plus 1, where n is an integer. Let's go ahead and check Wolfram alpha, because I think Wolfram alpha is going to offer the solution in a slightly different way. But don't forget what I got for the solution, okay? Make a copy. Now, ta-da-da-da. This is what Wolfram alpha gives us as a solution. I don't think it's correct, or did we make a mistake? Hopefully not. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.